Okay, so as chair of the session, I traditionally get the last speaking spot. So my name is Henry Segerman. I'm going to be talking about, this is all joint work with Saul Schleimer, who's at the University of Warwick. So the title of the talk is Sculptures in S3. Well, what's S3? So let's start with S2. So S2 is just the usual ordinary sphere in three-dimensional space that we all know. So it's the set of points that are at unit distance from the origin in R3. So by analogy, S1, the one-dimensional sphere, otherwise known as the circle, is the set of points at unit distance from the origin in R2. And so, of course, S3 is the set of points in R4, four-dimensional Euclidean space, the set of points at unit distance from the origin. So I want to do sculptures in this thing, and unfortunately it lives in four-dimensional space, which is traditionally difficult to work with. We'll see what's going on. So S3 is hard to visualize because it lives in four-dimensional space, but there's a trick that we can use. Well, one trick, there are many tricks. So the one that we looked at is called stereographic projection, which is a method of mapping from, in general, the n-dimensional sphere to Rn, which reduces the dimension by 1 because the n-dimensional sphere lives in Rn plus 1. So, for example, for n is 1, well, okay, so there's this function, so n is 1, the circle lives in R2, I've got a function that takes in x and y and it spits out something. This isn't very instructive, the picture is much better. So here I've got S1, which is living in R2, and here's R1, and I've marked the north pole of the circle here. And I'm just going to draw a line from the north pole, and it hits the line R1, it hits the circle. And the map from the circle to R1 is just, well, I'm going to map this point here on the circle to this point on the line, and it turns out that the coordinate of that is x over 1 minus y. And so here's another couple of examples. So here's a line, so I map from this point to this point on the line, and from this point to this point on the line over here. And one thing to notice at first is, as the points that you're mapping get closer and closer to the North Pole, their image in the line gets further and further out towards infinity. And so what happens for greater n, so this is, well, I can just tell you this is the cross-section of what happens for higher dimension. So if I just sort of rotate this picture around a vertical axis, I get what happens for S2, and so on. So let's see that. So for n is 2, again, there's this formula. It's basically the same thing, but the picture sort of makes more sense, maybe. So here's S2, the usual sphere. Here's R2, a plane that cuts through its equator. I've marked the north pole, and I draw a line from the north pole, and it hits the sphere in some point, and it hits the plane in some point, and the map goes from this point on the sphere to this point in the plane. So let's put some patterns on this. So here's the globe. This is approximately where we are, and if we were projected under stereographic projection, we would end up over here, somewhere on the eastern seaboard. Let's just zoom out a little bit. So you can see a couple of things here. So if you're on the equator and you get projected, you don't actually move. So if you're here somewhere in South America, then you don't move. You're still on the plane where it intersects the sphere. But as you sort of move north up here, you get very, very large and distorted. You get very, very big, close to infinity. So let's think of how we're going to use this. So let's imagine we're flatlanders and we want to understand a cube, a three-dimensional object. So here I've got a cube that's sitting inside of S2, and I want to use stereographic projection to make this cube part of R2 where I live. Well, so there's a problem because the edges of this cube go inside of the sphere, and so they're not part of the sphere. I can't project yet. So the first thing to do is make the edges of the cube onto the sphere. So I just blow everything up, project radially outwards. So now all of my edges are on the sphere. And then I'm going to use stereographic projection. It looks like this. And now I've got a picture that I, as a flatlander living in this two-dimensional plane, can understand. Now there's a problem. So where am I going with this? I want to 3D print things. So there's a sort of perennial problem is that you have to thicken things up. So you can't print one-dimensional objects, unfortunately. So these are one-dimensional lines, and I guess if I'm a flatlander, I need to print in two-dimensional objects. I can't do that yet. So let's start again. Cube, blow it up. But now I want to thicken it up here. So here I've thickened up those one-dimensional lines by taking neighborhoods in the sphere. and then I'm going to project this, and this is what I see. And you'll get these, you see that you get much thicker out here when you're nearer infinity. But there are some good properties that I'm going to mention now for why this is a good way to do it. So there's sort of two things you could imagine doing. You could either say, here's this one-dimensional pattern, I'm going to thicken it up in R2, or I can thicken it up when it's on the sphere and then project it. And I'm going to argue later on that thickening it up in the sphere is the better way to go. So what are some good properties of stereographic projection? So circles in the sphere map to circles in the Euclidean space. So you see these edges that I blew up. These are arcs of circles because they're living on the surface of the sphere, and they map to arcs of circles here, or possibly straight lines. So an arc of a circle here that goes through the North Pole maps to a straight line down here. A very important property is that it's conformal. That means that it preserves angles. So up here you see these three edges of the cube meet each other at 120-degree angles, and that's true here as well. And so what that means is that if you look at a local picture, if you look at just a small part of this, then this is an accurate picture of what's going on in the sphere. Globally, there's lots of distortion, but the local picture is correct. Bad properties of stereographic projection, particularly for printing stuff, is that as you get near the projection point, the North Pole, the things get very, very large, and so they can get expensive and difficult to print. So three-dimensional stereographic projection, well, it's just the same equation again. I'm not going to show you pictures because I can't draw stuff in 4 dimensions. Okay, so we've got some way of taking things that are in S3, bringing them into R3, and then we can print them and see what they look like. So what are we going to do with this? So we looked at a couple of different examples of kinds of objects, so 4-dimensional polytopes, and then surfaces, and I'll talk about both of these. And in both cases, we're going to come back again and again to this problem of needing to thicken up 1-dimensional or 2-dimensional objects into 3-dimensional objects so we can print them. So 4-dimensional polytopes. So 4-dimensional, these are the 6 4-dimensional regular polytopes. So these are analogs of the 3-dimensional regular polyhedron, the cube, octahedron, and so on. So in dimension 4, there are 6 of them. There's the 5-cell, otherwise known as the simplex or the pentachoron. Most people are probably familiar with the 8-cell or the hypercube or the tesseract. And then there's these other ones that I'll come to in a little bit. So we didn't bother with the 5-cell because it's kind of boring, so we went straight to the hypercube or the 8-cell. But before going on to that, let me just come back to that question of what's the best way to thicken things up so I can print them. So on the left, this is the hypercube thickened up in S3 before projecting to R3. And over here, I've thickened it up after projecting to R3. And, well, so there's a problem with this picture over here. So that's what I'm saying down here. So this is supposed to be a sort of symmetric picture. If I was really in S3, then this, say this square face here, would really be the same as this square face here. But here there's sort of a big difference between the thickness of this line and the distance across this square. It's a ratio of maybe 5 to 1 or something. Whereas the thickness of this line versus the distance across this big square here is something like 15 to 1. So you've somehow lost some symmetry, and that's not true here. Here the ratio between the thickness of the line and the breadth of the square is the same on all of the different squares. And so there are some symmetries that you retain of the object if you do this thickening up in S3 first, rather than doing it in R3. There are both pros and cons in terms of the cost and the strength of the printed object. So some of the more complicated ones, you can imagine you've got lines all over this thing. You've got in the middle a very complicated compact thing if you're using this thickening up in R3. And then around the outside, you've got very long, thin, spindly edges would be kind of weak. On the other hand, over here, you've got these huge fat things which are going to be very strong, but they're also going to be expensive. So you've sort of got some pros and cons there. Okay, so here's a picture of the hypercube and the tesseract. So this one has 16 tetrahedral cells. These are photographs of the 3D printed objects. They're down here. You can have a look at them afterwards. The 24 cells, so the 24 cell has 24 octahedral faces. So these are 4 different views. This is sort of just a generic view of this. This one, you can see there's this two-fold rotational axis, three-fold rotational axis, and four-fold rotational axis. And you can start to see, there's sort of possible problems with cost here, that these things around the outside are really thick. And this comes in at around $70 or $80, and you can't sort of shrink it down because there's, in the middle there's some very thin edges that if you shrink them any further you won't be able to print them. And that really becomes a problem when you move on to something like the 120 cell, which has 120 dodecahedral faces. And so way in the middle here there are some very thin edges relative to the outside. So there's a minimum thickness in 3D printing. You don't really want to go below a thickness of about 1 millimeter. And if you're at that scale, then the outside of this is, well, so the whole thing is around 30 centimeters across, with these very thick edges on the outside. It'd be very expensive to print. So instead, we're going to print something else. Well, we're going to cut it in half, and we're going to throw away the stuff that's near the North Pole. And so, because we're not printing that, then it'll be a lot cheaper. So how do you throw away the stuff near the North Pole? Well, you've got to find the equator. So in S2, the two-dimensional sphere, the equator is the circle around the outside, around the midpoint. In S3, the equator is actually a sphere. Here it is. It looks pretty small, because that's because this stuff around the outside is very near the North Pole, so it appears very big after stereographic projection. So we put in the equator, we cut it out, and this is what we get left. Let's just zoom in on that again. So same picture, put in the equator, which is a sphere, in S2, and cut it out. And then this is what we actually printed. And so this is very affordable, and it's still pretty complicated. So again, you've got these three-fold axis, two-fold axis here, and five-fold axis here. And the really neat thing about this is that you don't actually need to print all of the whole big thing. You can recover the whole 120 cell by taking this sort of a spherical boundary of this thing. If you just reflect this object across that spherical boundary, you recover the whole of the 120 cell. So you just have to buy two of these and then do the identification yourself in your mind, and there you go. You don't have to spend hundreds and hundreds of dollars on making this huge thing. And again, it's all conformal. Here's the 600 cell done in the same style. So this one's a particularly good reason to cut it in half. So with this positioning of the object in S3, there's actually a vertex of this at the North Pole. So if you stereographically project it and try and print it, you fill up most of the known universe with plastic. It gets very expensive and very difficult to find printers that are big enough. So here are some bigger examples. These are about 30 centimeters across. I wasn't paying for these, so it's okay to spend hundreds of dollars on them. But again, we're only doing half of them. At this scale, if you did the whole thing, it would be 5 meters across or something. Let me talk a little bit about duality. So there's, for polyhedra of any dimension, there's a concept of duality where you sort of swap vertices with faces and edges with edges and so on in 3 dimensions. So this is the cube, if you remember. And so what's dual to the cube? Well, most people probably know it's the octahedron. Here's how we see it. So let's put a vertex at the center of each face of this cube. There's another face out here, so really there should be some outside that's red as well. Haven't drawn that in. And you put an edge between each of those vertices, and what you've got then, the red edges are the edges of an octahedron. Let's just remove the edges of the cube, and so we just see the vertexes, one vertex in each face of the octahedron, remove them, and we just have the octahedron. And again, there's a vertex at infinity where these 4 edges link up, and that's the one skeleton, the edges of an octahedron. So what does this look like for 4-dimensional polytopes? So here's the hypercube, and this time there are these vertices, edges, faces, and 3-dimensional cells. So again, we'll put a vertex at the center of each cell. So there are 8 cubical faces of the hypercube. So 1, 2, 3, 4, 5, 6, 7. The 8th one is outside. That's where the background went red. We're actually inside or outside the 8th vertex. Let's put in the edges, and then remove the edges of the hypercube, and then remove the vertices of the hypercube, and this is the one skeleton of the 16 cell. So the hypercube and the 16 cell are dual to each other. So you can do this with the 24 cell as well. The 24 cell is actually self-dual. So the dual object is itself. Again, we've cut it in half because if you didn't, one of them would go through infinity. So this is a computer render. This is the plastic version. It's a little bit of a shame that there aren't two colors in the plastic version, but didn't get around to doing a color version of this. The 120 cell and the 600 cell are dual to each other. So here the blue is the half of a 120 cell, the red is half of a 600 cell, and so these are the objects in the exhibition. So there's the 120 cell, the 600 cell, and the 120 cell and the 600 cell, occupying the same space. It's a little bit confusing. If you sort of hold it in your hand, you can move one against the other and see that they're really two separate objects. Here's another idea. So here's the 120 cell again. The problem we had with printing the whole thing was we didn't want to print the stuff near infinity, so we cut some of it away. There were other ways of cutting this thing in half. So instead of cutting along a sphere, we can cut along a torus. And if you do that, you get this shape here. Here's the object. Here's a couple of other views of it. And you'll maybe notice there's a chain there's actually 10 dodecahedra going on in a chain in the middle of this. And then there's some sort of cut-off dodecahedra on the outside. So here's that chain of 10 dodecahedra again. And then there's another. It turns out that this chain is surrounded by 5 other chains of dodecahedra, 10 dodecahedra, which sort of surround it, and that forms half of the whole 120 cell. So there's a few puzzles that some of you have played with already. So these 3D printed, there are actually 3 separate rings in all of these different versions. There's this one, which again I've inflicted on a couple of people. So these 5 identical objects are just those rings with some of the bits cut out, and they somehow form together into this object which holds itself together just under tension. That's really fiddly to get it to do that. Okay, so now let's move on to surfaces. So we've done with polyhedra. So there's some surfaces and some other objects which you can represent in a really natural way if you take coordinates in S3 rather than in R3. And so I'm going to give some examples. So there's one example. So a circle is a very natural object in S3. Well, a circle is pretty natural in R3 as well. But so here's a way to write it down. So it's cosine alpha, sine alpha, and then the other 2 coordinates are 0. So we're somewhere in R4, and alpha is ranging from 0 to 2 pi. How do you check that this is in S3? You just check that the size is, the distance from the origin is 1. So cosine squared plus sine squared plus 0 squared plus 0 squared is 1, so it's lying on the 3-dimensional sphere. This is also a geodesic. So you can make a torus from the product of 2 circles. So I've got my cosine alpha, sine alpha, I've got a cosine beta, sine beta down here. So I have to introduce this factor of 1 over square root of 2, because otherwise I'm too big. So with just one of these circles, I'm big enough to be on the sphere, but if I've got 2, then the sum of the squares of these things is 2, so I have to have this factor in here. And so that's clearly a torus. It's called the Clifford torus, and it's a really natural object. This is just the same equation again, just so you can see it. Unfortunately, there's something slightly unsatisfying about this parameterization, which is that so if you fix alpha and vary beta, then you don't get a geodesic. You get sort of lines of so in the 2-dimensional sphere, the equator is a geodesic on the sphere, but the other lines of latitude are not. So they have some curvature. And so all of these guys have some curvature, which is not so nice. You can reparameterize, so I won't go into how you get this, but there's just some way to change variables and rotate things by 45 degrees, come up with another very nice form. And this time you do get geodesics if you fix theta and vary phi or vice versa. And there's another, okay, so before, you might think this is not a nice property. So this surface that I want to build goes through the projection point, the North Pole, but I actually want that to happen this time, and I'll show you in a second why. So this is what you get. So, well, okay, this is not quite what you get. So it's close to what you get. So I've got this surface, all of the arcs that we have here, this is fixing theta and varying phi or vice versa, they're all geodesics. So this goes to infinity, and we've cut it off again to save on costs. And so there's a really nice symmetry. So the reason we wanted it to go through the North Pole. So the torus the Clifford torus, it cuts the three-dimensional sphere into two parts. Each of them is a solid torus, and it turns out they're isometric. You can move one into the other, and it fits perfectly. And so with this projection point, that's true in R3 as well. So there's a torus sort of above everything here, and this, if I continued the surface outwards, it would sort of flatten out into a plane. So you get sort of above this surface is a solid torus, and below there's another solid torus, and you can rotate around in R3 to take one to the other. So there's another thing to say about this. So again, we had to thicken this thing up. How do we thicken it up? So we know we've got the parameterization of the surface. We've got the phi direction and the theta direction, but I need something in the third direction. I need to be able to move up and down to give it some thickness. How do you do that? Right. And again, so we want to thicken in S3 rather than in R3 because it retains more symmetry of the object. And so you need a normal vector to this surface in the 3-sphere in order to thicken. Now, if you were in R3 and you wanted a normal vector, you would just take the cross product of two vectors on the surface to get the third vector. You can't do that here because you're really sitting in R4. So how do we find a normal? Well, what you can do, so here's the position of a point, and I've got two vectors that are already in the surface. There's the derivative in the theta direction and the derivative in the phi direction. And these are both perpendicular to the position itself. So if you imagine one dimension down, you've got the usual sphere, and suppose you have, say, a path on the sphere, then the position, a vector going from the origin, talking about the position of a point on the sphere, and the tangent vector to a curve are at right angles to each other. And that's true here as well. So all you need to do, you've got these three vectors in R4, and you want one that's perpendicular to all three of them. And there's some standard ways to do that. So in the normal vector, you just take to be a unit vector, which is perpendicular to all three of them. And then so all we do is we move some distance away from the point that I'm talking about in this normal direction, and that gives me a way to say what thickness means. And so I can thicken up by a uniform amount in all by a uniform amount all over the whole of the surface, and I get these pictures. Here's a variant. So Carlo mentioned this is actually the same as the Sudanese Mobius strip. So it's just a very slight modification of this parameterization. So all I did here is there used to be a 1 here, and it changed to a 2 in these two positions, and then you get this, I guess we call it a round Mobius strip because the boundary of the Mobius strip is actually here. It's actually a round boundary. So again, just as in Carlo's talk, so this is the Sudanese Mobius strip. It's a slightly different version of this because we projected it to R3, again going through infinity, and that adds an extra little symmetry to what you see in R3 that you don't see in most pictures of the Sudanese Mobius strip. And as Carlo said again, if you extend the surface and you glue two copies of these to each other, you get a Klein bottle. Klein bottle has to intersect itself when you put it inside of R3, and in this case it actually intersects itself along a straight line. So you can see it going straight down here, and here you're looking directly down that line. There's a straight line that goes to infinity where the Klein bottle intersects itself. One further thing, so this isn't a surface, this is a knot. So again, in this case, this is a trefoil knot here, and it's just, again, we just changed this 2 to a 3/2, and this parameterizes this torus knot in a very nice way. So here, because it's just a knot, it's just a one-dimensional object, so phi is the thing that you vary here, and you just have to choose a value for theta. And again, you can thicken up. So we have these same local coordinates, theta, phi, the coordinates in this equation. You have a normal direction psi. And so you've sort of got this map from three-dimensional parameter space, this sort of domain, over to S3, well, and then to R3 again by stereographic projection. But then the point is that you can use these local coordinates to build little local decorative features. So here, all of these little cogs on this knotted cog. So these are all the same shape in the domain. They're the same shape in S3. It's only when we project, when we do the stereographic projection to R3, that the sizes of these things appear to be different. So these little cogs are the same size as these big ones. So I'm just going to talk about a few other projects that we're working on. So this is 2 interlinked Mobius ladders. This one we haven't printed it yet. This is 2 interlinked Mobius trefoils. Here are some versions of, this is a figure 8 knot, so the second simplest knot type. This is the one that I got out, well, that's down here. This is a version of sort of the complement of the knot. So you're supposed to imagine that this is a big ball, and we've drilled out this knot in here. We've been looking at, so these are this is a version of the Seifert surface on the trefoil. And just very recently we've been looking at, so these are Seifert surfaces on other torus knots. So I think this is the 3-4 torus knot, the 5-3 torus knot, and this is the 5-4 torus knot. We haven't thickened these up yet, so at some point we may renege on doing all the thickening up in S3, because it sort of gets difficult with this things being thick and things being too thin. It's either too expensive or it breaks. So that's my talk. This is me spray painting. So there's these are large 3D printed. This is the round Mobius strip, and the Klein bottle and the Taurus. These are going up in. If you ever find yourself in Melbourne, Australia, you should drop by the Department of Mathematics and Statistics and have a look at these. Thanks very much. Any questions? Yeah.
Yeah. How do you actually get these? How are they actually created by machine or?
Yeah. So it's all 3D printed. So they're designed on the software I use is Rhinoceros, and there's a Python scripting interface with Rhinoceros that you write the code and it generates the patches of surfaces which make up the boundary of what's going to be plastic. And you send it to a 3D printer and it produces these objects. Yeah.
What problems did you have providing the struts or whatever to hold isolated parts up?
Oh, so there's a couple of different 3D printing technologies. So the one that I'm using shapeways.com. So some of the 3D printing technologies, you build sort of scaffolding to support parts of the object that are sort of overhanging. With these ones, it's selective laser sintering. So you have sort of a bath of dust, and it sort of lays down a layer of dust and then zaps it with a laser to solidify it. And so everything's supported in this bath of dust. So you don't have those problems. So you really do whatever you want in terms of geometry, which is great. Yeah.
So in your example of projecting a cube in S2 onto a plane, you have the North Pole like directly over the center of the face.
Yeah.
And I was thinking, if you offset it, you'll get a different projection.
Right.
Did you try doing something similar in S3, or did that just look out?
There's a lot of all of that, in fact. I mean, so you have a choice of where to put the projection point. And the usual thing you want to do is put it in the middle of a face so that when it's projected, stuff isn't too big, right? I mean, the closer parts of the object are to the North Pole, the bigger and more expensive your thing is going to be. So you want to sort of put it in the middle of a face. But so with the dual 24 cells, you've got one of the two. If you put it so that the projection point is in the middle of the face, the other one goes directly through the projection point. So you sort of have to cut it in half or do something. But yeah, I mean, you can get all kinds of different versions of the same picture just by changing the projection point. Yeah.
So the trefoil knot is very symmetric, so it has that nice brown tradition. How hard is it to find a nice brown tradition for something like a figure 8 knot?
It's very hard. I mean, yeah. So there's a guy, Francois Guereteau, who I know, who came up with that parameterization of the figure 8 knot. I mean, you can make something, but you really want something nice and simple, or you want something that has some intrinsic geometry. And yeah, I mean, that's something we would really like to do. So these Seifert surfaces, these surfaces with boundary of the knot, we really want to do the figure 8 knot, and the math is very hard. Yeah.
Could we think about you put there the sphere, and everything inside of the sphere is less expensive than outside?
You mean the equatorial sphere? Yeah, because it's going to be smaller when you project.
But could you have an idea where you
Oh, you make it thinner. Yeah, you can. Yeah.
The morphing, which is somehow regular from inside to the outside.
Right.
And everything.
So I mean, so you can sort of, I mean, you can cheat in a way. So you lose the symmetry, but so this one here is pretty much the same thickness all the way through. It shouldn't be if I was thickening in S3. Here I'm cheating. I'm thickening in R3, just because it would be way too expensive to do it any other way. But yeah, you can certainly, if you break that rule, you can do lots of things. Okay, so I'm going to call it there, and Paul has an announcement to make.